Welcome to our new Omicron Lab video. My name is Britta and I want to show you today why it is so important to measure insulation materials over a wide range of frequencies using the dielectric material analysis instead of common methods like tangents delta at, for example, main frequency. To answer this question, I will take you on a journey through the basics of dielectric material analysis. Dielectric spectroscopy or dielectric response analysis is just a determination of the insulation properties of a dielectric material using a wider frequency range. As these properties are usually not constant but dependent on the frequency, the result is a characteristic curve when the properties are displayed. The ratio of lost energy to stored energy is the relative losses of a dielectric material, the tangents delta. From this measurement method, we derive tangents delta, permittivity, capacitance, impedance at different frequencies. When a dielectric material is placed in an external electrical field, charged particles are displayed. This process is called dielectric polarization. Depending on the frequency, different polarization phenomena occur. Electronic polarization, or deformation of the electronic shell, occurs due to the displacement of positively charged nucleus and negatively charged electrons in opposite directions, when an external field is applied and thereby a dipole moment is created in the dielectric material. Atomic or ionic polarization is caused by the relative displacement of positive and negative ions to each other. Electronic and atomic polarization have only a small influence to real part of the relative permittivity. These polarization mechanisms are almost lossless. Orientation or dipolar polarization is caused by alignment of permanent dipoles due to an electric field. The dipoles will rotate with the field direction. Hopping polarization is caused by movements in the hopping charge carriers. Interfacial and space charge polarization. Different dielectric layers with different permittivities and conductivities in one material can lead to accumulations of the charge carriers at the interfaces of the dielectric layers. The field distortion caused by the accumulation of these charges increases the overall capacitance of a material, which appears as an increase in real part of the complex permittivity. This can be seen in the lower frequencies from 1 Hz to microhertz, testing materials like composites or insulation surface skins. This slide shows why it is necessary to measure the whole dielectric response for an accurate material analysis. The measurement of the tangents delta at main frequencies allows just a very rough statement of the overall condition and no separation between different effects like changes in the material due to aging, quality or structure. As can be seen in the tangents delta at 50 Hz chart, the tangents delta value for the green and blue curve are nearly the same. It seems that the materials have the same structure and quality. But as can be seen in the second chart, only a wide frequency range provides enough data to differentiate between the different effects, making a full material analysis possible. With the dielectric response analysis, it can be easily seen that the green curve indicates that the dielectric material is aged in comparison to the blue curve. Many factors influence the dielectric response of a dielectric material, such as temperature, humidity or moisture, homogeneity, conductivity, for example, of oil, aging byproducts, viscosity, for example, during curing processes, or structure. From the graph, it can be seen that all those parameters influence the dielectric response curve in a different way. This can be used to separate those effects and to analyze, for example, the quality of the material during production, aging processes, curing processes, or electrical behaviors. In order to be able to perform such a separation, the whole curve has to be measured, from the kilohertz to the sub-millihertz region. Only if the curve is completely measured and the other parameters like epsilon or permittivity are analyzed. A separation of the effects and a correct moisture assessment is possible. Attention! Dielectric parameters are also influenced by the material itself and the sample dimension. Thus, we recommend to use the capacitance ratio of two frequency points, for example at 10 mHz and 50 Hz, in addition to the analysis of the curve and the result parameters, like permittivity, tangent delta, capacitance or impedance itself. This ratio is independent of material and dimension. These two curves also underline why it is important to measure over a wide frequency range. As can be seen in the first chart, it is often not enough only to measure the tangent delta. Polarization causes by aging processes often show the same curve changes and curve progressions like moisture in the dielectric material. A differentiation is only possible in the permittivity or capacitance chart. Beyond at the beginning of curing processes, an increased movement of charge carriers due to the molecule change is seen and results into polarization, which can be seen as a hump in the second chart at low frequencies. So, why is the dielectric material analysis so important? With the dielectric material analysis, a detection of aging or changes of insulation material structures or compositions is possible before the material is used in the field. Aging or changes of the dielectric material can lead into wrong electrical behavior, changes of electrical specification, reduction of dielectric strength, reduction of longevity, avoid short circuits, for example in high voltage equipment and thus faster aging, reduction of humidity or temperature stability. For a frequency range from microhertz to gigahertz, the following two measurement techniques can be used. Time domain spectroscopy, PDC, and frequency domain spectroscopy, FDS. There are more techniques like, for example, the AC bridges or reflectometer. The measurement technique for a dielectric material analysis depends on the frequency range to measure. The Omicron Lab dielectric material analysis, the Spectano 100, combines the time and frequency domain method in one device. There are advantages and disadvantages of these two dielectric techniques. The PDC measurement method is fast and accurate at low frequencies, but inaccurate at high frequencies. The FDS measurement method is fast and accurate at high frequencies, but very slow at low frequencies. Omicron Lab provides such a material analyzer with two dielectric spectroscopy techniques in one device, the frequency domain and the time domain. It combines the advantages of both techniques, fast and accurate at low and high frequencies. Together with the software and its accessories, it is especially designed for the analysis of liquid and solid materials to get more information about the material characteristics, polarization phenomena, structure or condition over a wide frequency range from 5 microhertz to 5 kilohertz. The key data and main benefits of the Spectano 100 are output voltages from 100 mV to 200 volt, PDC measurement current from picoampere range to 10 milliampere. Depending on the selected mode and frequency, an impedance range from 200 ohm to 20 tera ohm is possible. Capacitance range from 10 picofarad to 100 microfarad. A tangent delta range from 1 to 10. Test time reduction up to 75% by using the combined time and frequency domain mode. Flexible and easy integration by providing multiple adapters to connect to common test cells, and cables for temperature controlled environments from -55 degrees C to +250 degrees C. Thank you for watching the video. If you want to learn more about our products, visit our webpage.